All right, I know I'm a little bit late on this one, but I do still want to go through the last 6 learning outcomes and just kind of give you guys a big picture overview on everything that you kind of need to know going into the exams on these things. So, all right. So starting with 13, understanding the Laplace transform, you need to be able to you need to use the definition of the Laplace transform to compute the transform of basic functions and or piecewise functions built from these basic functions. So for example, show that the Laplace transform of t is like 1 over s squared. And part B, you need to use algebra skills and properties to compute the Laplace transform of linear combinations of functions in the table of transforms. So let's kind of look at some basic examples of what that could kind of look like. So like for your part A stuff, this is really just computing like the Laplace transform of basic stuff like e to the 2t, or the Laplace transform of 4t, stuff like this. So just by definition, the Laplace transform of a function is the integral from 0 to infinity of e to the negative st times that function integrated with respect to t. So for e to the 2t, it looks like this, and for 4t, it looks like this. Remember, it's sort of part of the definition that you have an improper integral, and so sort of baked into that definition is that you're taking a limit as b goes to infinity of the integral from 0 to b of whatever that function is. So I have been like kind of consistently a little bit picky about this. So if you don't have like limits in here, I do get a little bit picky about that. So make sure that you do kind of have the limit as b goes to infinity, that you're not like plugging in infinity into your thing, right? By the way, I probably wouldn't ask you anything more complicated than like either of these two things. So just kind of keep that in mind. For something like this, you basically just need to combine, just use exponent rules to combine these into the following: e to the negative st plus 2t, which you can then just kind of factor out of t, and then just kind of integrate this, and then take a limit as your upper bound b goes to infinity, right? And then this should give you, after simplifying, 1 over s minus 2. And then for problems like this, you're going to want to use integration by parts on this. So you'll make 4t your u, and e to the negative st your dv, and then just kind of go from there. For part B, you just want to basically use the table to compute basic stuff, but there's some algebra skills that kind of go into it as well. Like you might need to do the Laplace transform of t plus 2t squared or something like that. So whenever you see something like this, you want to kind of simplify the inside before taking the transform. So FOIL this out. This is t squared plus 4t oh, this is dumb. Let me maybe change that a little bit to like t plus 2 squared. Otherwise I could just like kind of combine the t plus 2t, and then it gives you 3t. 3t squared is like 9t to the 4th. Or 9, sorry, that should have been 9t squared, whatever. So anyway, something like this. The idea is FOIL it out, you get this. And then each of these parts, now you can compute their Laplace transform just one by one. Just sort of using the table, do stuff like that. So be able to use your basic algebra skills in order to do all that stuff. Yes, you do need to know how to use basic algebra skills in order to do well in this class. I know, shocker. But yeah, that's kind of the idea. So moving on to inverse Laplace transforms. So this is when we start actually using the Laplace transform. So this is, to me, like the big picture, but not too complicated learning outcome from this chapter. because it kind of uses all of the necessary skills in order to actually do something with it. And that is solve differential equations using the Laplace transform. Right? And so these IVPs are usually a little bit on the simpler side. And the Laplace transforms and inverse Laplace transforms that you need to do for these IVPs tend to be not too complicated. You don't really need too many formulas on it. You'll probably need to use some partial fractions here and there. That's kind of it. So yeah, so basically, I don't know if I'm gonna like do a whole problem here, but you might have like y double prime plus 4y equals 2, and maybe you have some conditions like y of 0 equals 1, y prime of 0 equals 0, something like this. Then, as always, like with these things, the idea is take the Laplace transform of both sides and then just try to basically solve for capital Y. So capital Y is by definition the Laplace transform of little y. Sometimes I'll write y of s or little y of t for capital Y or little y of t. So L of y double prime is just capital Y or capital Y of s minus y of 0s minus y prime of 0. That's just a formula that you guys should get. 4 times little y goes to 4 times capital Y or capital Y of s. And then the Laplace transform of 2 is just 2 over s. Then you want to like sub in like these things. So y of 0 equals 1. So this is 1 now. Y prime of 0 equals 0. So this will go away. This guy will just be 1 times s. And then these two guys, you can just kind of factor out a capital Y from both of them. Be left with, what am I doing? Yeah, I see. Okay, I messed up. This one should have been an s squared y of s minus y of 0s minus y prime of 0. This is what happens when I don't have the formula sheet in front of me, but okay. So yeah, this would give us s squared plus 4 left over if we factor that out. Okay, yeah, so this looks good now. And then minus 1 times s, and then like minus 0, don't usually write that. Equals 2 over s. Solve for y. So add s on both sides, divide by s squared plus 4. It'll look something like this. This is probably the part where I stop kind of doing it, but then your little y of t is going to be L inverse of this whole thing. L inverse of s over s squared plus 4 is going to be just cosine of 2t. So that'll be cosine of 2t. And then this guy over here on the right, this we're going to need to do partial fractions on. So in order to figure out L inverse of this, we want to do partial fractions, write that as 2 over s squared plus 4. So we want to write it as something over s plus something over s squared plus 4, where that something is always going to be the degree 1 less than the denominator. And then you'll just kind of do partial fractions on that. And then do L inverse of a over s and L inverse of bs plus c over s squared plus 4. This you'll probably need to kind of split up into bs over s squared plus 4. That'll be like a cosine of 2t kind of term. And then c over s squared plus 4, that'll be like a sine of 2t kind of term. All right, so I'll kind of stop there, but that's the main idea. All right, just keep scrolling down. 15 is one of the harder learning outcomes in the course. This is using all of the translation theorems to compute various Laplace transforms and inverse Laplace transforms, and using those translation theorems to solve IVPs using the translation theorems. So, all right, so the first one, maybe I should have had the formulas for this so I can kind of poke at stuff. Do I have them here? Maybe not. Surely I have it somewhere. Fall 22 final. Surely this would have the formulas at the bottom. Yeah, okay. Great, so here are the relevant formulas for that. Where did it? Okay, couldn't find that. There we go. All right, sorry about that. But here are the formulas that you need. So, so this first one is for the Laplace transform of e to the at times a function. You also need to know L inverse of stuff. So like the inverse of that that formula. And then here's the Laplace transform of just a function times u sub a. And then here's L inverse of that. All right, so so the first one's kind of straightforward. So if you have the Laplace transform of, let's say, sine of 2t, or let's do cosine actually. I like cosine better. Cosine of 2t times e to the 4t. So what is this? I should use the brackets. And the s notation, because this is a function of s, right? So by this formula, the Laplace of cosine of 2t times e to the 4t is going to be the same as the Laplace of cosine of 2t. But then instead of just having s's in there, it would be you plug in s with s minus 4. So replace all of the s's in the Laplace of cosine 2t with s minus 4. So cosine of 2t would be s over s squared plus 4. But then we replace all of our s's with s minus 4's. So this numerator becomes s minus 4, and then s squared in the denominator becomes s minus 4 squared, and then plus 4. Conversely, if you're doing L inverse of something, let's say you have, I don't know, 1 over s minus 3 squared plus 9, or let's do plus 16. So this almost looks like L inverse of just 1 over s squared plus 16, except it's a translation by 3 units because of this s minus 3 over here. So that tells you that your original thing had to have an e to the 3t in there. So this is like e to the 3t times L inverse of that guy, which this is almost like sine of 4t, so sometimes you'll need to like multiply and divide by 4. So times 4 and then divided by 4 on the outside. So this is like times a fourth of L inverse of 4 over s squared plus 16, which is just sine of 4t. So we get 1/4 e to the 3t times sine of 4t. Okay. U sub a, that one's a little bit trickier. So keep in mind, this is specifically for like when you have piecewise functions, or if I literally just write U sub a in the problem. So I could either, one, just ask you what is L of like U2 of t times like t, or something like that. So how would I do that? Let me not do t. Let me do something slightly. Let's do t squared actually. T squared's a decent example. So u2 times t squared would be what? So it's going to be, because we multiply by ua, this would be times e to the negative as. So this would be e to the negative 2s times L of f of t plus a. So this is your f of t, is your t squared, and then f of f of t plus a would be, just replace t with t plus 2. So t plus 2 squared. And then compute this Laplace transform. We'll have to FOIL that out first. This is t squared plus 4t plus 4. And I think we did almost this exact thing just not too long ago. This is 2 over s cubed plus 4 over s squared plus 4 over s. You should also know how to take the Laplace transform of piecewise functions using like U2. So let's say that I say f of t is equal to, let's say it's like t and then it's t squared. It's t if t is between 0 and, I don't know, let's say 4, and then it's going to be t squared if t is greater than or equal to 4. I'm gonna add another page in here. Okay. Then, all right, so what you can do is, well, remember, u sub 4 of t is equal to 0 or 1, depending on if t is between 0 and 4, or if t is greater than or equal to 4. And so you can write, so if you're trying to compute L of f of t, which is probably what the problem would be asking you to do, what you would start by doing is write f of t in terms of u sub 4. So this is equal to t plus u sub 4 times t squared minus t. So if you do this, so notice that if t is between 0 and 4, then u sub 4 would equal 0, and this whole formula would basically just give you t, which is what you want it to give you. Right? And if t is greater than or equal to 4, you want the formula to give you t squared. Now, if t is greater than or equal to 4, then u sub 4 is equal to 1. And so this formula gives you t plus t squared minus t. So the t's cancel out, and you just get t squared, which is kind of what you are, exactly what you're hoping for. Okay. So this is your formula for how to compute, how to write f of t in terms of u sub 4. And then to compute the Laplace transform, just gotta do the Laplace of t plus u4 times t squared minus t. So what's the Laplace of t? It's 1 over s squared. And then what's the Laplace of u4 times t squared minus t? Well, this would be e to the negative 4s times the Laplace of, and this is going to be where the f of t and then like f of t plus 4 thing, or f of t plus a thing, comes into play. So this will become t plus 4 squared minus t plus 4. So we get 1 over s squared plus e to the negative 4s times, and then expand all this out, t squared plus 8t plus 16 minus t minus 4, and then just compute that transform from there. I guess I'll simplify before taking the transform. It doesn't really matter. This would be like 8t minus t is 7t, and then 16 minus 4 is 12. And so we get 2 over s cubed plus 7 over s squared plus 12 over s. That's your transform. All right, and now lastly, you need to know how to do L inverse. So notice that anytime we do the Laplace of like u sub 4 times something, we end up with an e to the negative 4s, or e to the negative as popping up in our final answer. Now, conversely, if you do L inverse of something that has an e to the negative 4s in there, then that would tell you that there should have been like a u sub 4 of t in your starting answer. So if I see like an e to the negative 5s times, let's say like, I don't know, let's just do s over s squared plus 4. then that tells me, well, because there's an e to the negative 5s in there, then it would be, so applying the formula, e to the negative as times f is equal to, just do L inverse of f, but then evaluate at t minus a, and that final answer is going to be multiplied by u sub a. So do L inverse, plug in t minus a, and then times u sub a. So I'll put the u sub a first. So this is u sub 5 of t times, and then we'll do L inverse of s over s squared plus 4, and then evaluate at t minus 5. So this is u sub 5 times, all right, well, this guy goes to cosine of 2t, but instead of cosine of 2t, it would be cosine of 2, replace t with t minus 5, so we get this. So cosine of 2t minus 5. Note, you can always check your work by applying the formula for the Laplace transform of u5 times cosine of 2t minus 5. So this would, by the formula, u5 would go to e to the negative 5s, and then times L of, well, here's our f of t, and then we want to do f of t plus 5. So this would be cosine of 2. Now replace t with t plus 5. We get that. So in here, t plus 5 minus 5 is just equal to t. And so this is really just cosine of 2t. And the Laplace of cosine of 2t is just s over s squared plus 4. And so we get exactly what we were starting with. Okay. So that's just really checking our work there. Okay. All right, cool. That's enough from 15. It's definitely one of the harder ones. On to 16. 16 is not so easy either, because this one there's just kind of a lot of formulas that we sort of went over between 7.4 and 7.5. So you need to be able to apply the derivatives of the Laplace transforms theorem to compute various transforms and inverse Laplace transforms. So that was like if you have L of t times sine of t, or L of t times cosine of 2t. So if you do t times sine of t, this would be negative the derivative of the Laplace of sine of t. So this would be negative derivative of like 1 over s squared plus 1. And then you just need to compute the derivative of this. So derivative of, you might want to write that as s squared plus 1 to the negative 1, so that you could just do a chain rule on that. So the negative comes down, combines with that negative to make a positive, and then s squared plus 1 to the negative 2, and then times the derivative of s squared plus 1, which is 2s. You can simplify it if you want, doesn't really matter. You get something like that. For cosine of 2t, it's like pretty similar, just do the negative derivative of the Laplace of cosine of 2t, which is s over s squared plus 4. On something like this, you have to do a quotient rule. I mean, you probably want to do a quotient rule, I guess. You don't have to. There's other ways to compute derivatives, but yeah, that's the idea. For like the inverse of something like this, if I gave you, say, let's say I just like started with this guy and asked you what is L inverse of 2s over s squared plus 1 squared. Here you would kind of want to recognize this guy. You would want this to be negative the derivative of some f of s. And then to solve for f of s, let me write it like this. So this guy equals 2s over s squared plus 1 squared. And so based off of this, bring the negative to the right-hand side, right? And then to get rid of the derivative, just like integrate both sides. So f of s would be the negative of the integral of 2s over s squared plus 1 squared. And so you just need to integrate this guy. And if you integrate that, you'll have to do a u sub. U equals s squared plus 1. Du is 2s ds. And so this gives us negative 1 over u squared du, or negative u to the negative 2, which integrates to u to the negative 1, divided by negative 1. But then there's a double negative, so it becomes positive, or 1 over u, which is 1 over s squared plus 1. So f of s is 1 over s squared plus 1. And so this guy is L inverse of negative derivative of 1 over s squared plus 1, which therefore is t times L inverse of 1 over s squared plus 1, just by that formula, which is t times sine of t, which is what we were expecting to get because that's what we started with over here to get that guy. So we're just sort of reversing that whole process. Add another page here. Convolution theorems, part B. Convolution theorem says that the Laplace of f star g, where star is the convolution, not multiplication. This is equal to L of f times L of g. So this is actually multiplication. All right, so you need to be able to like identify a convolution of two things. So like if I say the integral from 0 to tau of, let's just say like cosine of 2, yeah, this is 0 to t, right? Yeah, 0 to t of cosine of 2 tau times sine of 3 t minus tau d tau. This inside thing right here is literally just the Laplace transform. Sorry, this inside thing is just the convolution of the functions cosine 2t and sine of 3t. And so you just kind of need to compute the Laplace of cosine of 2t, which is s over s squared plus 4, and then times the Laplace of sine of 3t, which is 3 over s squared plus 9. And that's really all there is to it. You just multiply those two Laplace transforms. If you do L inverse would be a little different. So if you have like 2 over s times 1 over s minus 2, so L inverse would be like, all right, well, if you have multiplication after Laplacing, I guess, then when you do L inverse, it should just give you the convolution of the L inverse of those two guys. So this is going to be L inverse of 2 over s star L inverse of 1 over s minus 2. L inverse of 2 over s is just 2. And then L inverse of 1 over s minus 2 is e to the 2t. You can always like reverse the order that you do a convolution in. So you usually want to put the simpler thing last and then the slightly more complicated thing first. And then you want to actually compute the convolution. So this is like the integral from 0 to t of e to the 2 tau times f of t minus, or this is like your g of t. So g of t minus tau would go right here. But g of t minus tau is just going to equal 2 because there's no like t to plug in over there. G of t is equal to 2, so g of t minus tau is also equal to 2. That's part of why I wanted to put the 2 second instead of first. And then integrate with respect to tau. All right. Integral of 2e to the 2t is literally just e to the 2t, or sorry, tau, not t. And then integrate from 0 to t. This is e to the 2 tau minus e to the 0, or just e to the 2t minus 1. And yeah, that's really all there is to it. So you need to know how to compute the convolution of certain things. You need to know that formula. I guess there's kind of a lot that goes into it, but that's what it is. Periodic functions, these ones are all kind of the same. So remember that the definition of the Laplace transform is 0 to infinity e to the negative st times f of t dt. But for periodic functions, instead of integrating from 0 to infinity, you can really just integrate from 0 to whatever the period is. So capital T is going to be the period, and then e to the negative st times f of t. So that inside thing stays the same, but then you integrate from 0 to t, and then on the outside you multiply by 1 minus e to the negative s times that period. Like basically you're usually just going to want to identify what the period of a function is, and then you're going to try to just integrate this thing on this, smaller interval. It's not an infinite interval, so you don't have to do any improper integral shenanigans. You can just integrate it straight up. With some of them, like maybe you have it's just like a repeating function like this. Maybe it looks like f of t equals like 3t on this interval right there. And then your period is maybe like you're going from like 0 to 5 and then 5 to 10. And the picture keeps repeating. So here the period would be 5. And then on the first interval, so you would have like 1 over 1 minus e to the negative 5s. Remember, capital T is your period, that's 5 here. And then integrate from 0 to 5, and then e to the negative st times this one would be like 3t in that case. All right, and then you just need to integrate that. Or maybe you have something that it's like sort of like a piecewise thing, in which case okay, so maybe your period is like 10 here. But then maybe at 4, from 0 to 4, it's like one thing, and then from 4 to 10, it's like a different thing. So maybe you have to break it up into an integral from 0 to 4, and then plus 4 to 10 to integrate on that first period. And then the last one, there's not really much to say about the Dirac delta function. The Laplace of the delta function, if you do the Laplace of t minus 5, that's e to the negative 5s. And then what's L inverse of e to the negative 7s? It's just delta of t minus 7. That's really it for D. There's not much to do there. You just kind of need to be aware of that. Okay, anyway. That's it for that stuff. Chapter 8, it's a little different. So 17 is just sort of the basics of that stuff. So you need to be able to determine whether something is a fundamental set for a linear system. The two things that go into that are one. So you'll start with a set, call it x1 and x2. And then this is for an IVP, say dx dt equals a times x. So step 1 would be to show that each xi satisfies dx dt equals a times x. So the left-hand side is going to be the derivative of whatever your xi is equal to. So just compute that derivative, and then the right-hand side is just going to be a times xi. So just matrix multiplication, matrix times vector. And then you're going to want to simplify both of those and then show that the right-hand side equals the left-hand side. And then you want to do that for each of these guys. So you'll do this twice. Do the left-hand side and right-hand side for x1, and then do a left and right-hand side for x2. And then the other thing you want to show is that the show that x1 and x2 are linearly independent. And the way that you typically do this is show that the Wronskian of x1 and x2 is non-zero. So remember the Wronskian, like if you have, I don't know, e to the 2t, and then negative e to the 2t for your x1, and then e to the 4t, and then 5 e to the 4t for, maybe let's put a 2 right there, for your x2, then the Wronskian is going to be the determinant of this guy. So you'll want to compute the determinant of this. This is going to, and then simplify it as much as you can to show that it's non-zero. So in this case, this would be like 5 e to the 2t times e to the 4t, which simplifies to e to the 6t because exponents add. And then minus 2e to the 6t times, 2e to the, it would be like negative e to the 2t times 2e to the 4t, and since there's a double negative, it becomes plus. So this becomes 7e to the 6t. And constant times e to the kt is always non-zero. And so once you get to this point, then you can generally just say, all right, well, that's non-zero. Do not stop at this step and say that it's non-zero. It is not obvious that if you have something like this, that it's non-zero. Please simplify it down to make it obvious. Yeah, I would say if you have like a lot of people get to the point where it's like 5t e to the 2t minus like a bunch of other stuff, and then just say, oh yeah, obviously that's never equal to 0. To me, it's like not clear that you know how to simplify that. So if it's not clear to me that you know that you know how to simplify, then I'm not going to give you credit for it. So please know how to simplify these things. That is definitely part of the learning outcome. You do need to know how to do basic algebra in order to pass a differential equations class, believe it or not. All right, determine whether a non-homogeneous linear system has a unique solution and the largest interval of solution, or the largest possible interval that the solution is defined on. So this is when I give you guys like a DE that looks like dx dt equals something times x plus some other vector over here. So this would be a non-homogeneous thing. And you have some entries over here and some entries over here. Maybe they're like 2 and then like 5 over t and then 2 over 3 minus t, maybe t squared, e to the t, and then maybe let's do like I don't know, 1 over t minus 2. And then I give you a condition, say like x of 1 equals 2, 3, something like that. So basically, there's a theorem that says if all of the entries of these two guys are continuous on a common interval, and that common interval contains whatever point you need to be able to plug in for your IBP, then you get a unique solution on that interval. So usually in my head, I'll like kind of list the points that we're discontinuous at. So 5 over t, this guy, and this guy are the only things that are not continuous everywhere. So we need to avoid t equals 0 for 5 equals t. We need to avoid t equals 3 for 2 over 3 minus t. And we need to avoid t equals 2 for 1 over t minus 2. So basically, we're just avoiding the denominator equaling 0. Okay, so just throw out those points on your number line and then figure out where is t equals 1. Well, that's right here. And then just pick the largest interval that avoids 0, 2, and 3 and contains t equals 1. And so obviously that interval is just going to be the interval 0 to 2. So all the entries are continuous on 0 to 2, and t naught equals 1 is in the interval 0 to 2. So there is a unique solution on that interval. That's their largest interval. And that's it. All right. And then the last thing is solving linear systems. So you just need to be able to solve various homogeneous linear systems. So usually, there's 3 cases. There's, so you have like dx dt equals a times x. So you could have, all right, tripping over my words here. So your steps are always going to be start by finding the eigenvalues, and you do that by taking the determinant of a minus lambda I, setting that equal to 0, finding your roots of that equation, right? And then there's 3 cases. There's either 2 real eigenvalues, in which case your solutions are just, in your fundamental set, they are x1 equals e to the lambda 1t times v1, where v1 is your eigenvector for lambda 1. And then lambda 2 comes with its own eigenvector, v2. All right, so you'll find an eigenvector for lambda 1 and an eigenvector for lambda 2, and then get your solutions just that way. And then your general solution is c1x1 plus c2x2. And if you have like an initial condition that says x of 0 equals like 3, 1 or something like that, then you'll just plug in t equals 0 into c1x1 plus c2x2. So plug in t equals 0 over there. Boop, boop. Set that equal to 3, 1. And then you'll probably have to do like some row reducing. So yeah, because if you plug t equals 0 into this guy, then you get e to the 0 times v1, which is literally just 1 times v1, or v1 itself. And then over here as well, that'd just be v2. And then you can put that into a matrix, row reduce, and figure out what your coefficients c1 and c2 are. Okay. There could be 1 real eigenvalue. So here, your solutions in your fundamental set are going to be, so let's call lambda the eigenvalue. So then you get e to the lambda t times v, where v is your eigenvector. So I'm just assuming that we've already found v. And x2 will be e to the lambda t times not v, and also not just t times v, but tv plus u, where u is a solution to a minus lambda I u equals v. And so this guy, so if a minus lambda I, this might look like 2, -3, 2, and then maybe 4, -6 or something like that. That might be your a minus lambda I. And then v could be like, maybe your eigenvector v is like 2, 4 or something. Then you would just kind of put 2, 4 over here, and you get this augmented matrix. And then you can row reduce this augmented matrix. And if you do it correctly, then your first row should just be whatever, and then your second row should be just a row of zeros. If you do not get a row of zeros for your second row, that is a huge red flag that you did something wrong, okay? So if this is like a 3 or something like that over here, you need to go back and find your mistake because there is one. It is impossible to get a row that is not all zeros unless you made a mistake at this point or up to this point. So if you do it right, in setting this thing up, you should be able to row reduce it to just some row for your row 1, and then your other row is just going to be a row of zeros. Maybe it's vice versa. Maybe row 1 is your row of zeros, and row 2 is just a standard row. But once you get it to this point, this is basically telling you that, all right, so u is equal to just like it has an x and y component, and then it satisfies the equation 2x minus 3y equals 2, okay? Something like this. So this is just coming from like the coefficients over here. And then you just need to pick an xy pair that satisfies this. So here, like maybe the easiest one to do would be, you know, pick y equals 0 and then solve for x. So that tells you like 2x equals 2, so then x equals 1. So then u equals 1, 0 would be a valid solution to that. Or maybe you do x equals, you know, pick like x equals 2 and then plug that in. Or let's say like x equals 3. Then you get 2 times 3 minus 3y equals 2. So this is 6 minus 3y equals 2. So solving for y, you get like a negative 4 over there. And then y equals positive 4/3. So then u would be 3 and then 4/3. Right, there's infinitely many solutions here. You just need to like pick an x value and solve for y, or pick a y value and solve for x, and just do it in a way that like hopefully gives you like easy enough numbers to work with. And then again, just like in the previous case, if you have like x of 0 equals 3, 1, you need to just plug in t equals 0 into your general solution, c1x1 plus c2x2, and then solve for those coefficients c1 and c2. And then the last case is when you have two complex eigenvalues. So with this, all you have to do is, so write your eigenvalues as a plus or minus bi. All you have to do is find one eigenvector, call it v, for a plus bi, and then write v as like u plus I w, where u and w only have like real entries in it. So you're splitting it up into like a real and a complex vector. So like for example, if you have v equals 2 plus 3i and then 7 or something like that, you would write this as like 2, 7 plus I times 3, 0. Okay, and then this would be your u, and then this guy would be your w. And then there's literally just a formula for what these solutions are going to be. I'm probably just going to go back to a formula sheet from that old final. Diffie-Q. Final exam from spring. This should be good. Should be on here somewhere. Yep, okay, here it is. So these guys right here. Just copy that, bring it up here. And there you go, and these are going to be your solutions here. So, so like if your a plus bi is like 4 plus 7i, 4 plus or minus 7i, then a is 4 and b is 7. So this would be like e to the 4t times 2, 7 cosine of 7t minus w, which is 3, 0, sine of 7t. That's going to be your x1. And then your x2 would be just sort of like just plug into that guy, right? So same idea. And then if you have like, again, like x of 0 equals 3, 1, then you just plug in t equals 0 up here. So e to the 0, so like x1 of 0, c1 x1 of 0 plus c2 x2 of 0. I'll show you how this one works out a little bit better. Let me actually finish writing down my x1 and x2. So this is e to the 4t times 3, 0 cosine of 7t plus 2, 7 sine of 7t. And if we set this equal to 3, 1, so if I plug in t equals 0 to this guy, this is like x1 of t. Plug in t equals 0, e to the 0 is 0. And then 2, 7 times cosine of 0, and then minus 3, 0 sine of 0. And then plus c2 e to the 0, 3, 0 cosine of 0 plus 2, 7 sine of 0, right? But sine of 0 is equal to 0, so that's 0, that's 0. E to the 0 equals 1, so, and then cosine of 0 equals 1. So this whole thing just becomes c1 times 2, 7 plus c2 times 3, 0. And then this is all equal to 3, 1. So then you could just put this into a matrix and row reduce. So 2, 3, 3, and then 7, 0, 1, and then just row reduce. So the numbers here, obviously I just picked randomly, so they're not going to work out very nicely. Maybe let me change it from like 3, 1 to like 3, 14 or something like that, so that it works out nicer. So I'm just changing the problem here. Okay, so then if you get something like this, so this row right here tells you like 7x equals 14, 7x plus 0y, or 7x equals 14. So I could just take that row, divide it by 2, so then 1, 0, 2. So that's telling us that x equals 2, right? And then you can do negative 2, row 2, add it to row 1. So that becomes a 0, that becomes unchanged, and then negative 4 plus 3 is negative 1. And then we can divide that row 1 by 3. And so that tells us that, so 0 c1 plus 1 times c2 equals negative a third. So c2 equals negative 1/3. And then similarly, 1 times c1 plus 0 c2 equals 2. So c1 equals 2. And then we just got to plug c1 equals 2 and c2 equals negative a third into this solution up here. So it would be, this is your c1, that was 2, and then your c2 is negative a third. So do like negative a third up here. And then obviously these should all be like t's again for your general solution, but yeah. Maybe I'll just write it down just because I can, I guess. Ah, jeez. All right, so you get 2 times x1 minus a third times x2. And that's it. Okay, cool. So this one's kind of a little bit more on just kind of using the formulas that are given to you. The formulas are kind of gross, so I'm not going to like ask you to recreate any of these formulas or tell me where it comes from. Just kind of seeing if you're able to use them effectively. But yeah, that's it. So hopefully this helped. I'm going to stop rambling now. And yeah, good luck on studying. Sorry, this is a little bit late, but hopefully it is still helpful to some of you. All right, take care, guys.